Good morning. Happy Friday. Hope you all are doing well today. This will be our last live class of the module as everything is due tonight. And then Monday, we start on some new material. So I've been looking through the stuff that's been turned in so far. So far, it's been really, really good. Great job on article reports, on your experiment proposals. I'm excited to see the experiments that you do. And so for next week, the main thing that you're going to do experiment-wise is your at-home experiment that you've proposed, assuming everything goes okay. Now, because it's a 2-week module, we've got a little bit of time. But as I said before, please don't start your experiment if your proposal hasn't been approved yet, because I want to make sure that you're choosing safe things that also meet the goals. The ones I've seen so far have been great. And we have made a couple changes to things like safety-wise where that had to happen, but mostly it's been all good. So again, the experiments that you choose don't have to be anything complicated. Doesn't have to be a college level whatever, because a lot of times those are meant to be done in labs and therefore not safe to do at home. They can be fairly simple. What's going to be interesting is how you change things in the process of finding things out. And that's what we're going to talk a little bit about today. How do we apply the scientific method? What does it actually mean to do science? And how does what you do in your at-home experiments, in your investigations, how does that end up being science? And how can you make it as interesting and as useful as possible? All right. So today, this is kind of the layout. I'm going to go through this idea of definitions of science using the articles from the that we were supposed to discuss this week. I think we're probably not going to have any kind of graded discussion on that. It's just I don't want to do the discussion board thing, and I just feel like it's going to be too much of a mess to try to organize it. So we'll talk about the ideas. We'll think about the ideas. Defining science is an objective of the class, so it'll show up on a quiz next module. But the discussion will be more informally. If you have questions, we can talk about it in Discord, but there won't be required postings or anything like that. All right. So then I'll just remind you again about what's coming up, and then if there are any questions or things that you are concerned about so far, there will be plenty of time to ask those questions if you're tuning in live. Otherwise, I'll take your questions on email or Discord as usual. All right, so let's get started. I am looking at the chat, so if you have questions, you can post them as we get into the stuff. All right, let's look at what is science here first. So to do that, I'm going to pull up these articles that you have read this week. And I think the most useful ones in defining science are the first and the third one, the Feynman one and the one from Science for All Americans. So we're going to look at that a little bit. The one from Einstein is interesting because it's from a famous scientist, but it's a little bit more about thinking about science in opposition to other things, and we'll get into that in a little bit. All right, so I like the way that Richard Feynman defines science in this article, and it comes in let's see. Got to find it here. It's near the top. I know this seems like a long article, but it's not difficult reading, and I think it'll be really helpful in how we think about these things. So please make sure you do go through it if you haven't yet. All right. I'm getting there. Okay. So there's a nice paragraph right here that starts, "What is science?" So we can start with that. And one of the things that I like about his definition here is that he talks about that it's really three things or a mixture of them. So let's look at those three things, and then we'll think about how that applies to us and what we're doing in our experiments. And you, as potentially non-scientists, why is it important to understand these three definitions and how to use them? So first, science can be a way of finding things out, sometimes known as the scientific method. So a way of getting knowledge. All right. Second, it can be the actual things that you find out. So the rules, the laws, the ways of explaining the natural world can be thought of in science. And then the third way, or the third definition, is sometimes it is the things that you can do after you have found something out. And I would agree with Feynman here that that's actually better known as technology. That is how you apply what you've learned about the world to then control something. And the reason that it's important, I think, to think about this in three parts is we often think of science as only that last thing. Science is technology. Science is like what we can do. We can build stuff, we can fix things, we can, all of that stuff, that's science. That's not really science. That's a different thing. That's technology, that's engineering, that's applying what we know. If we take an example like in the news today, we're talking about vaccines for COVID. And everybody's saying like, yay, science has made the vaccines. I mean, kind of, yeah, but it's not the vaccines that are really the science. The science is what's been done over the last 50 years or more to understand what viruses are and how they work. I guess like 100 years. So viruses have been known about for about 100 years, give or take. So you've got all this time of just learning stuff with no real obvious application, how these different these different methods work to grow different types of proteins and cells, stuff like that. These all of that has been thought of just by people who were curious and explored by people who were curious about those things. And yes, we see the results of that now in the technology, but it was really the science that was done before that that allowed for that to happen. All right. So so maybe let's write this down. So we can think of science as a method, a way of finding things out. We can, whoops, hold on, you can't see this. There we go. We can think of it as a body of knowledge. Stuff we know about our world, about the natural world. And we can think about it as the applications, which is maybe better known as technology. So how we use what we have learned to develop new things or to control our world in some way. All right. So in the article, Feynman goes backwards through these. He talks about technology first and what that is, and some of the challenges with technology. So let's take a look at that. We're actually going to spend more time on the other one. So let's just kind of look at what he talks about. Now, for him, science is purely objective. And I would say, writing this in the, I want to say the 60s or 70s, that was a reasonable position. I think probably nowadays we would say that is in question, that science is not purely objective, but rather something that is done by people and therefore necessarily subject to the, fix this here, subject to people's interpretations, to people's biases and all of that. So in Feynman's view, science is, as he says, a key to the gates of heaven that also opens the gates of hell. And in this analogy, he's saying basically the technology, the applications are in themselves neutral, and they can do great things and they can do terrible things. And his example is with nuclear technology. He worked on the Manhattan Project, which developed the atomic bombs during World War II. And like most of the scientists was very ambivalent about that. Should we be doing this? Should we be developing that? At the time, it seemed like a good idea, but then afterwards, the scientists involved had a lot of doubt once they saw all of the death and the horror that their inventions caused. So this idea that the technology that we develop using science can be helpful, it can also be hurtful. And for Feynman, he sort of pushes that away and says scientists don't really have any responsibility there. That all rests on the politicians, on the community to decide what they want to do with the technology. And, that's something you can think about, something we would normally discuss. What do you think about that? I think that personally, as a scientist, I think we have more responsibility than that. I don't think we can just say, let's develop all this stuff and, if somebody uses it for bad reasons, well, it's not our fault. I think we have to live our values a little bit better than that. And I would encourage you to do the same. If there are things that you care about in the world, you don't want to work against those values, whether it's your job or whatever. So that's his take on technology. And then I think he spends his most time and the most sort of exciting and beautiful writing for him talking about the second part of science, which is the method of finding things out. The second one, which is the body of knowledge, what you can actually figure out by doing science. The things you can discover about the world that were previously unknown, and sometimes wrongly known, and then we were able to use the method of finding things out, the scientific method, to actually discover things that are in some sense true. So, as he says, I'll just read an excerpt here. The next aspect of science is its contents, the things that have been found out. This is the yield. This is the gold, the excitement, the pay you get for all the disciplined thinking and hard work. The work is not done for the sake of an application. It is done for the excitement of what is found out. And I'd say this is true for most scientists. We see a lot of focus on the applications, but the things that really drive people into science are often just that idea of coming up with a beautiful new rule of explaining something about the world that was previously not known or not understood in that way. And in that way, chemistry is truly a liberal art. In that way, just like poetry, the goal of poetry is not to do a particular thing. The goal of poetry is to create something beautiful that was not known before. And I think that's the same with science, that really the goal there is to make a beautiful explanation of what's happening in the world. And the rest of it, the technology, is kind of just gravy, just something else we can do to make it even better. So, you can read that part and talk a little bit about that. All right, so then on to the method that is really most applicable to what we're doing in our class. We're probably not discovering anything brand new. Maybe if you do, let me know if you do, that would be awesome. But we are going to use the scientific method to try to figure some stuff out. So, let's look at that. What does that mean? So, you probably in a previous class, you learned about the specific steps of the scientific method. That's all fine. But we want to talk about it a little bit more generally here. So what Feynman says, this method is based on the principle that observation is the judge of whether something is so or not. All other aspects and characteristics of science can be understood directly when we understand that observation is the ultimate and final judge of the truth of an idea. All right, so in this way, he's kind of defining science only to its particular domain. And Einstein talks about this also in the paper where he's talking about it against religion, that the scientific method is only applicable to things that we can observe. And by observe, that's a broad term. It doesn't just mean see with our eyes, but it means that you have to be able to collect data on whatever's going on to be able to figure it out and to be able to show evidence as to why something is true or not. So then, as Feynman says here, the principle that observation is the judge imposes a severe limitation to the kinds of questions that can be answered. They're limited to questions that you can put this way. If I do this, what will happen? And then you can try it and see, right? And so questions like, should I do this? And what is the value of this? Are not really scientific questions. Scientific method can't, you should do something. It can tell you if something causes something else, those sorts of ideas. And so I think that we see a lot of issues here in things like what we call pseudoscience, stuff where it is a little bit harder to show this cause and effect. So in large domains where you have lots of conflicting variables and you can't really isolate things very well, so stuff like education, sociology, economics, where there isn't clear cause and effect, there's just too much data. There could be other confounding things going on. The scientific method is often applied to those situations, which is okay, but it always have to be taken a little bit more carefully than something like in the chemical or the physics domain where you can really do those experiments. And then there are other domains where it absolutely does fit this question. If I do this, what will happen? And yet it is still thought of as or people still believe the wrong thing. So for example, for a long time, there was a group of people, I think they're still out there, who believe that vaccines have negative consequences, like they can cause autism or something. That's something that can be proved. Like you can collect evidence. You can look at everybody who's got vaccines. You can take data and you can you can figure that out from the data. And time and again, it's been shown that that link does not exist, that they do not cause these negative effects like whatever. And there's a different question, that is autism even really a negative effect, right? Because it's just a normal way of being in the world. But nevertheless, that link is not shown value free. The link has not been shown scientifically. So that's where we kind of have an issue in modern scientific interpretation, is when we have used the correct method to come up with reasonable rules from the data that can be shown, that can be proven in this particular way, and then people are still going to just not believe it because they don't want to. So I would encourage you. Certainly, we have that with like COVID stuff as well, right? That if the science is clear that this particular thing works, and a bunch of people are still like, nah, I don't believe it. So when you are thinking about these things, or when you're talking with your families about these things and your friends, I would encourage you to think about those separate domains. Think about what can be known and what can't be known. What is more of like a should question, and what is more of a what do we know question. And the should questions are things that we can disagree on, that we can have debates, that we can have conflicting politics around. But what actually is should be something that we can all agree on by looking at the data. All right, so there's another important part about making these observations in science, and it has to do with this idea of doubt. So knowledge creation has changed over the centuries. Where we get our knowledge from has changed. So pre-science, before the scientific method started to be developed in the 1600s, of course, people were always doing science. Indigenous populations had methods of finding things out that were essentially scientific, even though they were defined in a different way. So we don't want to purely say that science was a modern European invention, because that's not true. But our modern idea of science before that in places like Europe, then the predominant way that people got knowledge was through authority. So somebody in charge, a king, the pope, whatever, would say, this is the truth, and people would say, well, they're in charge, they're the authority, therefore I believe what they say, and that must be the truth. And so the thing that was so revolutionary about the scientific method was that it doesn't require authority. You don't have to listen to me tell you some scientific concept is true. You don't have to believe me. You can actually go find it out for yourself. You can do the tests, you can do the experiment, and you can show that it is indeed true. So the idea of authoritarian knowledge, that I know something, or that the king knows something, or that whoever the church knows something, and therefore you believe what they say, that's no longer true when you have a way of testing things and actually seeing if they're true or not. And that's why people like Galileo, got in trouble, because they questioned that authority and they said, well, you're saying this, but my experiments show the opposite. I have all this data to show that you're wrong. And authorities don't tend to like that. So luckily, we have, I would say, gone in the more scientific direction that is more democratized, that anyone can do. But of course, we still have problems with authority, and we still have issues with people believing things based on what authorities tell them, even though they can be easily disproven. All right. So the other two articles are kind of echoes of this point. This one from Einstein doesn't really deal as much with the definitions of science, but it talks a little bit about his ideas with regard to science and religion. Einstein's relationship to religion was complicated and changed a lot throughout his life. And so if you have those kinds of questions, or you've thought about these kinds of things, this is a nice way of kind of thinking about his thoughts of how these things work together. And to him, he again, it's complicated, and he went through a lot of different phases in his life with this. But generally, he takes this separate domain idea as well, that once a problem gets big enough and value-based enough, science really can't help you there, because the question is just too big. There's too many different variables. So you have to think about something else to help you make those decisions. And there's various choices there, one of them being religion. But he does argue against some of the ideas of like the ways that certain religions can try to assert things about the physical world that can be easily refuted. And so he doesn't kind of buy into those. All right. So here's our three ideas of science and some of the background there. I want to give you two other definitions that are really important, are going to be really important going forward, and are often misinterpreted. So in these definitions, they're often really confusing for students. So I want you to kind of focus on these so that we can be clear and we can be on the same page with them. And they are law and theory. Now, the reason these words cause so much confusion and trouble is because they have different definitions in science than they do in our everyday general lives, not outside of science. And because the same words are used in two different situations, that causes problems, because we have our normal definitions and then we have our science definitions. So let's focus on our science definitions now, and then let's think about why they're so different. So in science, a law is, hold on. Okay. In science, a law is a set of observations that generally well, let's see. If we talk about cause and effect, for a law, we're generally talking about the effect. So if we have, if this happens, then this happens. When this happens, this happens. So the law of gravity, when two masses are around each other, they attract each other by this particular ratio, the equation for gravity. So that's a set of observations. Now, notice that I didn't say it is something that is absolutely true. So here's the misconception. I'm not going to write it down because it's wrong. But most people think, and it's okay if you do, because most people do, most people think that a scientific law means something that is absolutely true and has been proven to be 100% true. And that is not the case. A law is a set of observations where when one thing changes, something else changes in the same, and it seems to happen like that most of the time. And it requires evidence, so you have to show that this actually is true. And also, importantly, it can be disproven. A law is not absolutely always true. If you find enough evidence, you can actually show that it's not quite right. And an example of this is Newton's laws of motions, which aren't wrong. They are correct, but the laws that Newton came up with to show like how projectiles move and things, they break down in they stop working in certain situations, like when things are really, really small, when things are going really, really fast. Then Newton's laws of motion don't quite work right, and we have to use things like relativity and some quantum mechanics and stuff like that to explain them. So it's not that he's wrong, but his laws were only really applicable in certain situations, and so some bounds had to be put on them. So that's a law. That's a scientific law. It's a set of observations that shows what happens. A scientific theory is an explanation. Sorry, my pen's being a little squirrely here. Explanation the explanation behind what happens. So we can call this the why or the cause. So for example, atomic theory is the theory that matter is made up of atoms, tiny little atoms. And because of that, if that is our explanation, then we can explain a bunch of like why matter works in particular ways that it does because of this theory. So again, a theory requires evidence. A theory can also be proven or can be disproven, so there always has to be some doubt about that. But notice the difference here. Laws and theories talk about different parts of the knowledge process. Law is the set of observations. So I keep every time this happens. And theory is, well, here's the atomic law or the atomic concept or whatever that is causing that to happen. Here's another example then. Maybe the law is that every time it is, let's say, good example. Every time people buy lots of ice cream, let's say this, every time people buy lots of ice cream, the beaches are crowded. All right, so people buying lots of ice cream is correlated to crowded beaches. That could maybe be that's an observation that could maybe be put into a law. But it doesn't tell us that the buying ice cream causes beaches to be crowded. And it doesn't say really why that's happening. So we could have a theory of the ice cream and beach correlation that talks about how when it's really, really hot out, people want ice cream, and when it's really, really hot out, people want to go to the beach. And so that causes those things to both, the rates of those things to increase at the same time. So that makes more sense, right? If it's hot out, that's what's really causing things. And so that's our theory behind it. The law was the set of observations, and the theory was the explanation behind it. So notice that this is very different from what most people think, which is that a law is something that is proven true, and a theory is something that is like just some sort of general idea that isn't proven yet. And that is wrong. And that comes from our non-scientific definitions of these words, that a law is something that has been like written into government, and a theory is sometimes just like somebody's idea. That's a definition of the word theory. But in the scientific context, a law applies to a specific thing and a theory applies to a specific thing. They can both be as true or as false as the evidence that supports them. So that's in a keep straight for you all, that we're talking about different things when we talk about laws and theories. So when someone says, oh, that's not really true, that's just a theory, that's not, they better not be talking about the scientific context, because that's not what law and theory mean in the scientific context. All right, checking if anybody's on Discord here. No, looks good. Okay. So before we move on, are there any questions about science, scientific method, definitions of theories and laws, anything like that? All right. Well, let's take a look at Blackboard again to look at stuff that's due tonight, if you haven't done it already. Sorry, just waiting for Blackboard to load here. Okay, I don't know what's going on with Blackboard. It is seems to be stuck. But I think I can just tell you. So it is, we've got read the articles. There's the article report, which isn't about the articles we talked about today. The article report is for the article that you find from a newspaper or something like that. And then you can follow those directions there, and I'll look through and give you some comments. The ones I've seen have been great so far. Make sure you do your observations lab for the paper chromatography from your lab kit. And then there's also the safety training stuff. So make sure you watch the safety video and keep taking the safety quiz until you've got 100% on that. Why I can't seem to get to Blackboard right now, but frustrating. Anyway, get it on my phone. Well, you can see the assignments there, and let me know if you have any questions. So just a reminder of the format of the class. Everything's due tonight, Friday night, and there's nothing to do this weekend. So the next module will come up on Monday. I might open it up early as soon as I finish it and make sure everything's good, like today or tomorrow, but I don't actually want you to get started on it. I want you to take a weekend. We all need to take some breaks, and I want you to do that. So, I know we have to plan things out. If you want to get stuff done early, that's okay. But I would encourage you to just take the weekend off and get ready to get started again on Monday. The at-home experiment proposal is also due, so I'll be also working through the weekend on trying to get those reviewed so that you can start your proposals. But with the number of people in the class, I don't know that I'll get through all of them, since a lot of them are not in yet. So I'm assuming there's going to be a big load of them tonight. I will get through them as soon as I can, but I may not get to yours by Monday, so just hold off on that and do some other stuff before you start your at-home experiment next week. Okay, I did get this to load, so let me open this up again. Yeah, so question, do you pick your own experiment? Well, so there's two different experiments to do. There's the experiment from the lab kit, the observations paper chromatography that we went through on Monday night. That's kind of prescribed as in the module. For the at-home experiment proposal here, so you've got your chromatography lab, that's from the kit. The at-home experiment proposal, you're picking your own thing that you want to do at home. And so while we're talking about that, let's bring in what we just learned about the scientific method. So the idea is, for the at-home experiment, you're not just going out and finding a procedure and following that procedure. You're starting with that, but then you want to do something to try to figure out what's going on. So for example, one experiment that was proposed so far, if I can think of one, was like a soap making experiment was proposed. So the original proposal was to actually make the soap from fats, from lipids, from like oils, because that's how soap is made. And we actually do that lab on campus. But I said to this person, sorry, you can't do this at home. It's too dangerous because it uses lye, sodium hydroxide, which is really, really corrosive. And you have to heat up this corrosive chemical with the oil. And it's just too risky. It's something we really need to do in the lab. So I said, well, okay, that's not going to work. So they said, okay, well, I'm still interested in soap. Can I try this other one where I'm just taking already made soap, basically like a soap, kind of mixing it with other stuff, melting it, and adding other ingredients. And that, I said, yeah, that works. But you can't just follow the directions and make some soap. The idea is that you change something, that you say, okay, well, what does this ingredient do? What does this ingredient do? Let's see what happens if I use more of this, or let's see what happens if I use less of this, or change the temperature a little bit. So you're changing some variables and then thinking about what that teaches you. Based on Feynman's definitions, the first way of science is you're thinking about how you can change things to try to figure out what these different ingredients do to the soap. The second definition, what you learn from that, is like, how does it turn out? Oh, this kind of ingredient does this to it. This kind of ingredient, makes it greasier. This one makes it harder. This one makes it more brittle. Those kinds of things. And then the third part, the technology, is now you know how to make soap exactly the way you want because you used the scientific method. You tested some different ways of doing things. You learned how these different things affect the final soap. And then you can use that going forward to figure out how to make soap exactly the way you want it. So that was just an example of how the at-home experiment proposal might work. So that's the idea, is that you want to change something so that you learn about what's going on instead of just following the directions as you see them and then calling it good. So you're not actually doing that experiment this week. You're proposing it by tonight, and then you are performing it next week after your proposal is approved. All right, other questions? Yeah, exactly. So they don't need to be like some super fancy, tricky experiment. It can be something super basic, like for kindergartners, but you need to think about ways that you can change it so that you can learn something about that experiment, like how it works, what causes what. All right. Well, while I'm asking about questions, or while you're thinking about your questions, also keep in mind, since we're all online now, I'm getting a ton of emails and yeah, you're welcome. I'm getting a ton of emails and messages and stuff from various parts of the college, and so if I don't answer you, like like within a day or so, just send it again. I'm never gonna get annoyed that you're bugging me. You're my students, you're my highest priority. I want to talk to you and I want to answer your questions. But sometimes stuff just gets lost and I miss stuff. So if you're not hearing back from me, just keep sending. Give me a day or so to respond and then send again and say, hey, I just had this question. Hey, I just had this question. I'm sure I'll see it eventually, but I have lost a couple messages here and there, and I felt bad that I didn't get back to people. So if you have a question and you're trying to reach me on Discord or email, and I'm not getting back to you, just keep sending it. And if it's a couple days I'm still not getting back to you, chances are something's wrong, and maybe I'm not getting the message. Maybe you got the wrong email address or something. Just again, to review ways to reach me, you can email me. My email address is here, and it's on the syllabus. It's in the faculty information on Blackboard. You can message me on Discord, either a direct message or in one of the channels. Don't call me. There's no one in my office. I probably won't get that message. And then you can also book a meeting with me. So you can, like, there's no more for this week, but next week you can just like pick some day, and you can pick a time, and this will synchronize with my calendar. So if I have other meetings, those times will automatically go away. So you can just pick a time and put your name and say book, and I'll get an email and a calendar notification, and I'll meet you in my WebEx room to do that. So that's another way of reaching me if you want to talk one-on-one over the computer. All right. Well, let me know if you have more questions. Otherwise, have a great weekend off. Hopefully everything goes okay with getting your assignments in tonight. If you have questions about the assignments, just to let you know, I go to bed usually around 10. So after that, I won't be answering any questions before stuff is due at midnight. But I'll be around today, and I'll try to get questions answered as quickly as I can. All right. Well, thanks, everybody. And I will see you Monday night, where we will look at next week's stuff for the first time. So I'll see you then. Bye.